Hi, and welcome to my talk on extractor lower bounds. My name is João. I'm a third-year PhD student at Imperial College, and this is joint work with Divesh Agarwal, Xiao Guo, Maciej Obramski, and Noah Stevens-Davidowitz. And the topic of this talk is randomness extraction, which in short is the art of converting weak sources of randomness into nearly uniform randomness, which is fundamental for many tasks in computer science. And the basic motivation for our work is the following probable randomness extraction task, where we start with a weak source of randomness x, which is a k-source, meaning that all we know about it is that it contains at least k bits of min-entropy, or in other words, that the probability of any of its outputs is upper bounded by 2 to the minus k. And this is a very relaxed and very standard assumption in the randomness extraction literature. So the goal of probable extraction is to design an extractor with d seeds, such that for every fixing of the seed 1 through d, it outputs a block y1 through yd as a function of x. And we want that at least half of these blocks should be close to uniformly distributed, in the sense that the statistical distance between the marginal distribution of the block and the uniform distribution on m bits should be at most some epsilon. So tasks of this type show up, for example, as an important step in constructions of multi-source extractors, which are objects that extract nearly uniform randomness from multiple independent weak sources. And there the bottleneck is the number of seeds required for probable extraction. So if we can accomplish probable extraction using fewer seeds, we can improve the constructions or improve the parameters of multi-source extractors and also simplify their constructions considerably. So it is then natural to want to understand what is the minimum number of seeds required for probable extraction. And this problem feeds into the more general classical problem in pseudo-randomness of determining the minimum number of seeds required by different types of extractors. And what we'll see in the rest of the talk is that by starting off with this question, this will lead us to many interesting results. And deriving these results will require the development of new lower bound techniques that we believe will be useful in other settings. Okay, so to begin with, let us discuss the naive solution for probable randomness extraction, which is actually used in all the previous works on multi-source extractors. And this naive solution is to just use a strong-seeded extractor, which is a special type of extractor with many applications in cryptography, for example, with the special property that for any k-source x, if we pick the seed at random, then the expected value of the statistical distance over the choice of the seed is small. And it is easy to see that this indeed solves our problem of probable randomness extraction. And so in order to evaluate the performance of this naive solution, we can ask what is the minimum number of seeds required for a strong extractor. And this turns out to be a very well understood problem, and it is known that the minimum number of seeds for strong extractors scales like n minus k over epsilon squared. And the upper bound comes from the probabilistic method. The lower bound was proved by Radhakrishnan and Tashma. So we know that if we want to use a naive solution, then we need at least n minus k over epsilon squared seeds. So then the natural question is, can we do better than this for probable randomness extraction? And one first observation is that, of course, the naive solution is overkill because achieving probable randomness extraction is equivalent to designing what we call a probable extractor, which satisfies the weaker requirement that less than the delta fraction of the seeds have statistical distance larger than epsilon. So then, understanding the minimum number of seeds for probable randomness extraction is equivalent to asking what is the minimum number of seeds required for probable extractors. And in this talk, in our work, we focus on the most basic probable extractor, which we call a somewhere extractor, which corresponds to setting delta equals 1 in the definition of a probable extractor. And so a somewhere extractor, the only requirement is that the minimum of the statistical distance over all the seeds for any k-source should be at most epsilon. And of course, any lower bound on the number of seeds that we prove for a somewhere extractor carries over to all other probable extractors. So we're just going to focus on the somewhere extractor. So to have a clear picture of the differences between strong extractors and somewhere extractors going forward, we'll compare them side by side. So a strong extractor has a property that the expected value of the statistical distance over a uniform choice of the seed for an arbitrary k-source should be at most epsilon, while a somewhere extractor only has the weaker requirement that the minimum statistical distance over all the choices of the seed should be at most epsilon. And for strong extractors, we have a good understanding of the minimum number of seeds. We know it scales like n minus k over epsilon squared. However, for somewhere extractors, we don't know much. So we have some lower bounds. For example, we have this lower bound that depends on the output length of the extractor, but this lower bound is trivial when the output length is small, in particular when it is just 1 bit. And making a parallel with strong extractors, we would like to have lower bounds that are independent of the output length of the extractor. So for the rest of the talk, we'll just focus on the case where m equals 1, or in other words, the somewhere extractor outputs just 1 bit, because lower bounds in this setting carry over to all output lengths. So there is a non-trivial lower bound that is independent of the output length, but it is very weak, because the best upper bound that we know for somewhere extractors is exactly the same upper bound as for strong extractors of n minus k over epsilon squared. So now the question that we really want to understand is whether somewhere extractors can beat strong extractors, in the sense that do they require much fewer seeds than strong extractors. So if we're trying to answer a question like this, the most natural thing to do first is to study the upper bound given by the probabilistic method. So we know that for strong extractors, the probabilistic method gives the optimal upper bound on the minimum number of seeds, and this is actually true for many other pseudo-random objects like multi-source extractors and randomness dispersers. So it is natural to wonder what kind of upper bound the probabilistic method gives for somewhere extractors. And as our first result, we are able to pin down exactly what kind of upper bound the probabilistic method can give. And we show that if we take a random function with n minus k over epsilon squared seeds, it will be a somewhere extractor with high probability, and that this actually cannot be improved because we prove that if we take a random function with significantly fewer than n minus k over epsilon squared seeds, then it will not be a somewhere extractor with very, very high probability. And so, essentially, with the probabilistic method, we really cannot get a better upper bound than n minus k over epsilon squared. So, the natural question here is this upper bound of n minus k over epsilon squared optimal for somewhere extractors, as it was for strong extractors and for other pseudo-random objects where the probabilistic method is optimal? So surprisingly, we are able to show that this is false because we are able to beat the probabilistic method in some regimes. So we in particular show the existence of a somewhere extractor where the number of seeds scales like 1 over epsilon, while in comparison the probabilistic method would give 1 over epsilon squared seeds, which is much larger. And this holds when the min-entropy requirement for the weak source is very large. In particular, this implies that, surprisingly, somewhere extractors require much fewer seeds than strong extractors. And so the naive solution that is used for probable extraction is actually suboptimal. So what I'll show now is just some intuition about how we construct this somewhere extractor that beats the probabilistic method. So we start here with the input space of n-bit strings that we see as integers from 0 to 2 to the n minus 1. And what we want to imagine is that to every seed, we associate a line that divides the input space in half, where according to whether some input is mapped to 0 or to 1 for that fixing of the seed. So for example, if we just have one seed, we would have the input space divided like this. And when we have two seeds, we arrange the lines so that they divide the space into 4 slices of the same size. And the output of the somewhere extractor inside each slice is constant because it is fully determined by just on which side of each line a given input is. So we can generalize this in a straightforward way to more seeds. So for 3 seeds, for example, we would just arrange the 3 lines so that we get 6 slices of the same size, and the output of the somewhere extractor is constant inside each slice. So this can be formalized, for example, by defining the function to be, say, the sign of x plus I modulo 2d, where I is the seed. And we see the the output of this modulo operation as an integer between minus d and d minus 1, and the sign just returns 1 whenever this integer is non-negative. So the way we prove that this function is indeed a somewhere extractor is through the pigeonhole principle. So what we want to show intuitively is that if we take an arbitrary k-source x, there exists at least one line from the ones we see here that divides the mass of x almost in half. So this happens if the number of seeds is large enough. So what we show, first of all, naturally we can just define the bias of the ith line to be just the difference in the probability mass of x on either side of the line. And so what we show is that if we set the number of seeds to be appropriately large, in this case to be roughly 2 to the n minus k over epsilon, then we can show that the difference in the bias from one line to the next is always very small. And essentially, since the biases must change sign at some point, the pigeonhole principle implies that there must exist one line for which the bias is very small, which indeed shows that this function is a somewhere extractor with the desired properties. Okay, so now that we have this somewhere extractor with 1 over epsilon seeds, the natural follow-up question is whether we can do much better than this or whether this is already close to optimal. So in order to answer this, we will study lower bounds on the minimum number of seeds. And one thing that we should note is that previous lower bound techniques are not applicable to somewhere extractors because they are highly tailored to settings where say that the output is uniform with high probability over the choice of some seed. So for example, as was the case for strong extractors. So we need a new approach towards lower bounds, and this is what I'm going to describe here. So first, we must set some notation. So for a given extractor x, we're going to define its output on some input x to be just a concatenation of all its outputs for every fixing of the seed. So the output will be a d-bit string, because we're focusing on the setting where the extractor only outputs 1 bit for every fixing of the seed. Okay, so in order to derive lower bounds, we want to design for each extractor a distribution P over the output set that satisfies two very obvious conditions. The first one is that P should be sufficiently biased, and the definition of bias obviously depends on the type of extractor we're considering. So for example, for strong extractors, we would like that the expected value of the statistical distance over a uniform choice of the seed, or equivalently the coordinate of P, should be larger than some appropriate function alpha. While for a somewhere extractor, we just want that the minimum of the statistical distance between Pi and the uniform distribution over all the choices of the seed I should be larger than some appropriate function. And second, we want to show that there exists some k-source x such that P is the output distribution of this k-source x according to this extractor. So of course, it is very obvious that if we have these two conditions at the same time, then we obtain a lower bound on the error epsilon of the extractor. In particular, we get that epsilon is at least alpha. And so this can be rearranged to get a lower bound on the number of seeds of the extractor. So the problem here is that satisfying either one of these conditions by themselves is trivial, but it is very difficult to try to do both at the same time. Especially if we look at condition 2, the most natural way of ensuring that condition 2 is satisfied is to first design a bad input k-source x and then consider the associated output distribution. But if we do things this way, then it's very hard to make sure that condition 1 is also satisfied with a large enough function alpha. So the novelty in our approach is that we show that condition 2 can actually be phrased in a very simple way if we define this distribution P with respect to a special distribution A, which is the output distribution of the extractor on a uniform input string. And so in the lower bounds that I'll show you for the rest of the talk, we'll always define P to be some scaling of the special distribution A, which makes verifying condition 2 a very simple task, and then gives us more freedom to make sure that P is sufficiently biased. So the takeaway message from here, from this slide really, is that this distribution A, so the output distribution of the extractor on a uniform input, is a very important object for deriving lower bounds and will be the main object that helps us derive optimal lower bounds for the rest of the talk. Okay, so the first lower bound we show is an optimal lower bound for somewhere extractor. So we are actually able to show that every somewhere extractor must have at least roughly n minus k over epsilon seeds, and because of the upper bound that we have already seen, we know that this cannot be improved in general. So it cannot be improved, for example, when k is very large. So, like I said in the previous slide, the starting point for our lower bound is this special distribution A, which is in this case, it is the output distribution of the somewhere extractor on a uniform input string. So, for the talk, I'm just going to focus on the setting where, still non-trivial setting, where A is assumed to be a uniform distribution over d-bit strings. So in this case, like I said before, we'll define our distribution P to be a scaling of A. In this case, P will just be the product distribution with some bias gamma. So this is a distribution over d-bit strings, and gamma is some constant to be determined. So what must we show? Well, first we must show that, well, P gamma is biased enough. And this basically comes from the fact that every coordinate of P gamma is sufficiently biased. And this is very easy to see because we know that from the fact that P gamma is just a product distribution, the probability that any one of its entries equals 0 is always 1/2 times 1 plus gamma. And so the bias at every coordinate of P gamma is always exactly gamma over 2. So if we can show that P gamma is the output distribution of some K source for a decent value of gamma, then we obtain a lower bound on the error epsilon of the extractor of gamma over 2. But because of the simple condition that we identified before, and because P gamma is a scaling of our distribution A, verifying condition 2 is just equivalent to a very simple inequality in terms of gamma, d, and n and k. And this inequality is satisfied if we choose gamma to be of the order of n minus k over d. So combining these two properties gives us a lower bound on epsilon of n minus k over d, and we can rearrange this to get a lower bound on d of n minus k over epsilon, which, as we've seen before, cannot be improved in general. So as a bonus, using our new lower bound techniques, we are also able to recover the optimal lower bound for strong extractors with an alternative and much simpler proof. So recall that what we want to show is that every strong extractor must have at least n minus k over epsilon squared seeds. And again, just like it was the case for somewhere extractors, the starting point is the special distribution A, which is the output distribution of the strong extractor on a uniform bit string, which is represented here in this circle, with the blue dots being the mass points of A. So in general, what we will do is that we're going to define P as the restriction of A to a Hamming ball of radius r around the origin. So for this talk, we're just going to focus on the non-trivial case where we assume A to be uniformly distributed over d-bit strings. And in this case, P will always be a scaling of A, and it will be just a uniform distribution over the radius r Hamming ball around the origin. So the reason why we choose our distribution PR like this is that proving that PR is biased is now very simple because it is a straightforward application of the triangle inequality. So using the triangle inequality, we can show that the expected bias of PR across over a uniform choice of the seed is at least 1/2 minus r over d, meaning that if we choose the radius r appropriately, we get a lower bound of square root of n minus k over d on the expected bias of PR. Okay, so this would give us the desired lower bound on the number of seeds, on the error of the strong extractor, if we can show that PR is indeed the output distribution of some K source. But similarly to what happened in the case of somewhere extractors, because we define PR as a scaling of A, showing condition 2 amounts to just verifying a very simple fact. So verifying condition 2 is just equivalent to ensuring that the volume of the Hamming ball that we're considering is large enough. And this is an immediate consequence of the fact that the Chernoff bound is tight. And we also use the fact that we have a special choice of the radius r. So if we have these two conditions, then we get our lower bound on the error of the strong extractor of square root n minus k over d. And we can rearrange this to get a lower bound on d of n minus k over epsilon squared seeds. So we've reached the end of this talk, and I'd just like to quickly recap what we've seen and leave you with some very interesting open questions. So throughout this talk, we are interested in studying the minimum number of seeds required by some natural variants of strong extractors. So this question for strong extractors themselves was already well understood. So we know that the minimum number of seeds for strong extractors scales like n minus k over epsilon squared. But even then, using our new lower bound techniques, we're able to give an alternative and much simpler proof of the optimal lower bound for strong extractors. Then, using our new techniques, we're also able to give a clearer picture of the minimum number of seeds required for somewhere and probable extractors. So we gave a lower bound of n minus k over epsilon seeds for every probable extractor, and using our upper bound, we're able to show that this lower bound is actually optimal in some regimes, namely when the min-entropy k is very large. Not only that, but our upper bound also has other very interesting implications. For example, it shows that the probabilistic method is suboptimal for somewhere extractors, which is surprising because the probabilistic method is optimal for strong extractors and many other pseudo-random objects. And also, our upper bound gives a fundamental separation between strong and somewhere extractors, because it shows that somewhere extractors require significantly fewer seeds than strong extractors. So our work still leaves open some very interesting questions. So for example, can we prove that our lower bound of n minus k over epsilon seeds is actually optimal in all regimes? Or in other words, can we give an upper bound of n minus k over epsilon on the minimum number of seeds for somewhere extractors for every k and epsilon? And also to complement this, can we get explicit constructions of somewhere and probable extractors with nearly optimal parameters that improve on strong extractors for the probable randomness extraction task? So this concludes the talk. Thanks for listening, and bye-bye.